Hey, this is Josh from LeetDev, where we explain programming questions as simple and concise as we can. Today, we're going to do something a little bit different, and we're going to talk about a nifty new data structure called a trie and some of its real-world applications. The trie data structure doesn't really show up often in interviews, but if it does and you know it, you'll really wow your interviewer. So our goal in this problem is to implement a trie. It's spelled T-R-I-E, but it's pronounced trie. We want to implement the trie with three APIs: insert, search, and starts with. So a quick example to familiarize ourselves with the API. Inserting just inserts a word into our trie, and then if we search for that same word, apple, it returns true. However, if we search for another word like app, which matches apple, it returns false. However, if we use starts with instead of search, it returns true because in our trie there is the word app inside because we inserted apple. This problem assumes that all of our inputs is from the letters A through Z, but I'll be a bit different and assume that we can have any English character. So without any delays, let's learn what a trie is and how to implement this. A trie is essentially a tree where we have nodes that connect to other nodes. The only difference versus a binary tree is that a trie is technically an n-array tree where we can have as many children as we want. Each of the children would be a unique letter that we would build up on to form words. For example, I have three words inserted inside our trie. We have apple, which as you can see is right here, A-P-P-L-E. We have the word apps, and notice how apps, we actually reuse the existing letters that we inserted. We have A, P, P, and then because there is no S children now in our apple, we insert S in. And then finally, we have the word Java. And because our root node over here doesn't have a letter J, we insert J in, insert A in, add V in, and then finally add the last A in. And that's essentially what a trie is. It's a quick way for us to look up letters and words inside a data structure. One of the best applications of tries is an autocomplete feature, similar to how you might search for something on Google. For example, if you type in LeetDev on Google, you might find a matching word. LeetDev is awesome, LeetDev is great, LeetDev like and subscribe. And to accomplish this, a trie allows us to quickly scan through and find similar words that matches our initial pattern. At this point, you might wonder, well, if we're just searching for words and we want to do it quickly, can't we just use a map or something? And you're right, we certainly can implement a map, and it would probably give us around the same constant time lookup. However, using a map can be far more expensive space-time wise. Consider that we build up a word of apple and apps. If we want to have the capability to do a quick lookup, we need to store all the letters that map with A, which is apple and apps, all the letters that map with AP, APP, and APPL, and so on and so forth. And while this could be a bit computationally faster because we can just grab the words directly, it becomes a nightmare for space complexity if we have a set of large amount of words. Versus if we use a trie, we only need to keep track of each of the letters once. We might have to scan through more words to identify numbers. However, we don't have to store every single possible letter and map that to every single possible matching words in comparison. And that is why a trie is superior in terms of dealing with large word sets. Now that we have an idea of what a trie is, we can start implementing one. Like a binary tree, all tries need to be represented by a data structure. That data structure is just a node. Probably call it a trie node, but for the sake of space, I'll just call it a node. A node consists of two things. It contains all of its children, which we will be storing in a map. And this can be like A, B, C, D, and each of the children would have its own children of characters to node. And each of the nodes have a boolean called isEnd, which can be true or false. This is important so that we know if a string of characters is a word that we inserted in, or it's just a collection of letters that was used to build up a word. For example, if we have For example, if we have O and B, we have Bob. We might be able to find Bo, but Bo is not an actual word we inserted in. It could be useful for finding search prefixes, as in when the user types in BO, and then we can see what other words are associated with it. But we won't be able to identify that we found a word until we find a node that has isEnd to be true. The first API we want to find is our insert operation. To accomplish this, we first need to create a temp current node and set it to be the root. And that is what we have right here. In our trie data structure, we are guaranteed to have a root because we can define our constructor ourselves. And so we define an empty root to start off our whole tree. For our insert operation, let's say we're adding a word, let's say app. All we have to do is we have to iterate through each of the letters in our word and check if the letter exists in our map. If it doesn't exist, we need to add a mapping between the character and a new node. In this example, let's say we're inserting a in for our app. So we check in our current and we see that current does not have any children. So we create a new map and we associate a with our new trie node. Note that we don't actually have a node that contains the letter it is currently at. Each of the nodes would have a mapping to other nodes based off of what letter it corresponds to. However, I'm just going to draw the letters on the node to represent what it is. After we inserted the node, we set our temp node to be the node associated with our current letter. So we just get the children for A, and then we set current to be that node. And then we basically just repeat the process until we reach the end of the word. So the next letter would be P. So we make P because it doesn't exist yet. And then we move our current to be that node. And then we do that one more time. Move current down. And one thing I forgot to mention is that once we reach the end of our word, on the last node, we want to make sure that we set the isEnd to be true, so that we know that we insert the word app inside our trie. The runtime of this algorithm is O of n because we are storing every letter of our word into our trie. The spacetime complexity of this is also O of n because worst case scenario, we have not built up a word at all and we have to store every single letter inside our data structure. Continuing from our example, let's say you want to search and we want to search for the word app. We would do the exact same thing. We would create a temp node that would iterate through our trie and we would set it to be root. Then we would iterate going through each of the letters to see if they exist in our map. If it doesn't exist, then we return false. False. Otherwise, we just continuing and we set our temp node to be the node of the current letter we're at. And then we just keep going until we reach the end of our word. And then we just check to see if our node that we're at has isEnd set to be true, meaning that we've inserted that specific word. So next example, current is set to root. We check to see if our first letter A is a child. It is. So we set our current to be that node. We check to see if P is in our children of A. It is. And then we check to see if the P, again, is a child of our current node. And it is. And then we've reached the end of our word. All we have to do now is check if the current node that we're at has isEnd set to be true. In this instance, it is. So we return true. Now, there's another API called search prefix that we need to implement. It follows this exact same logic. The only difference is that we have to make sure we reach the end of our word and we just return true. Now, the runtime of both search and search prefix is O of n because worst case, our word is inside our trie, and so we have to scan through every single letter. Spacewise is constant time because all we're making is a temp node that we'll use to iterate through our root. Now that we understand the high level, we can get to the implementation. In our code, the first thing we want to do is we want to define our node. So we quickly made a node data structure. It has two fields, children, which is that mapping between the character and the node that's associated with it. And we have the Boolean isEnd, which we set if the specific node we're on is the last letter of a word. We create a public constructor where we would initialize everything. And if we were good programmers, we would actually set up APIs that would interact with these objects. We don't necessarily actually want to expose these two fields that we set. However, for ease of use, I decided just to make them public. So now that we define the node, our trie node that we want to iterate, we need to initialize our actual trie, which we'll be calling our insert, search, and starts with API. A very easy implementation. We just create a field called root, which we initialize to be our first trie node. And now we need to start implementing our 3 APIs. The first thing we want to handle is insert. So what we did here is we created our cur temp node, like we talked about earlier. We would iterate through all the letters inside our word. We do that by converting our word to be a char array, and then we just iterate through all those, getting the chars. Then now that we have the letter, we just check to see inside the map of our current node, which is our children, to see if there is a existing mapping for the letter that we're on. If it doesn't, so that means we need to create a new node to represent this letter. Now after we create the node, or possibly not, we just set our current node to be the node of the letter we just inserted in. And then we just keep continuing this, adding nodes if it doesn't exist into our trie until we reach the end. And then we just set the isEnd boolean to be true, because this node that we're currently on represents the last letter of our word. Next, we need to implement search. Our search API is very similar to our insert. First, we create a node, which we would use to iterate through our trie. And then we do a for each loop of all the letters inside a word. We check to see if the current letter is a children of our node. And if it isn't, that means we have not inserted that word, so we return false. Otherwise, we set our node to be the current children of the letter that we're looking for, and we just continue our algorithm. And once we reach the end, and assuming that every letter matched, we just check to see if isEnd is true. If it's true, that means we have inserted the word inside of our trie. Otherwise, that means we just encountered a string of letters that just happened to be the word that we're looking for. And then finally, we have our starts with function, which is actually very similar to search. In fact, it's so similar that I'll just copy and paste and make a minor adjustment. We just check to see if our trie contains every letter in our word. If it doesn't, then we return false. Otherwise, once we reach the end, we just return true because we know that we found the prefix. And that's it. Let's hit submit. And there you go. This is how you implement a trie. If you found this video helpful, consider hitting the like button and maybe even subscribing to get updates. Otherwise, I'll see you in the next video and have a great day.